so the first postulate is about the minimal universal coupling of a curve geometry G mu nu of x to matter, the matter of the standard model, and we explain connections at length. And I did not have the time to explain, although you have seen it already in Jacob's talks and in Hermann Nicolai's lectures. The second postulate of GR is now talking about the propagation properties and the self-interaction properties of the gravitational field itself, described by a metric G mu nu, and it is given by the Einstein-Hilbert action with all its coefficients. So I remind you, G is minus the determinant of the metric G mu nu, and then you have this Ricci scalar where the Ricci tensor R mu nu is obtained by contracting two indices in the curvature tensor with four indices. So the sign convention is that the first term in the expansion of the Ricci as distinct with a plus sign, then there are three more terms. So I wrote again explicitly what is the formula for the curvature tensor. When you look at it, it always looks a bit complicated. You have to remember that in my convention, the differentiation index, which is, for instance, nu for the first time, is always last. And when you differentiate here with mu, the differentiation index will be always the last on this gamma symbol. And the other things are put like ordinary matrices. A simple way has been discovered by Cartan to understand the structure of this object, which is that if you introduce not only the connection, the linear connection, but the one form associated to the linear connection, here in coordinates where you contract the last index by an infinitesimal displacement in space-time, and then you consider it as a Cartan one form omega alpha beta, then the two form associated to the curvature tensor. So this curvature tensor has two indices which are like matrix indices acting on the vectorial indices, and then it has indices linked to differentiation directions in a two-plane. This is simply given by the formula d omega plus omega omega with very simple matrix indices put in the normal order. And this is linked, and it is the same as the formula for any gauge theory where the curvature, the field strength, when you write it geometrically with a gauge potential A considered both as an abstract Lie algebra element. So I don't write the Lie algebra index. I don't write the mu index, which is contracted by a dx mu to make it a one form. And then the formula is just dA plus one of the Lie bracket commutator of forms and also Lie algebra elements, which would mean 1/2 of this term minus the other term, but it's already antisymmetric. That's why there is no 1/2 here. And let me repeat, because the fact to call spin connection when you use the connection in a frame is sometimes a bit confusing. It is the geometric connection. It is always the same connection. When you have in a manifold, you have some vectors at a point in a tangent vector, the tangent space. You want to know how to parallelly propagate a vector here to a vector here. And it is, if you use the vectors represented in ordinary natural coordinates, the connection is given by this gamma. If you represent the vectors in terms of some frame, orthonormal or not, then it becomes the Ricci rotation coefficients, which is what Hermann called the spin connection, but it is the same connection geometrically. And that's why this formula is always the same. That's why the two curvature tensors are always the same. Another useful formula that sometimes you have to do is the commutator of two covariant derivative acting on the vector field up here, let's say, is the Ricci, is the curvature tensor with a plus sign. This morning, it's consistent with the formula written by Hermann this morning. The indices was done, but the indices here were put in reverse order. That's why the sign is consistent. I remind you also that the general definition in general relativity of the stress energy tensor of the matter is like Jacob wrote down, except that Jacob was using here minus sign and here the inverse metric, but you can just put the metric down and then you have a plus sign. there is a factor 2, there is the square root of the determinant of G, and this is the functional derivative of the Lagrangian with respect to G mu nu. When you have fermions, you have to go through intermediate Vierbein to do the calculation, but at the end you get this object. And then the total action of generativity is the action for gravity plus the action for how the standard model is coupled to gravity. And if you do the variational derivative of this with respect to the metric, then, and this is a homework exercise, that if you want to do the variation of this thing with respect to the metric, you will have two types of terms. The terms that you obtain by varying algebraically the metric here and here. And these two terms, the first term by varying this, give this object with a minus sign. The other term, because it's the inverse metric, this term gives the variation of the determinant, and that gives the 1/2 square G mu nu delta G mu nu times R, where R is this object. Okay, R is the scalar curvature. So this term comes from varying only these two terms in Einstein action. And then the exercise is to prove that when you vary this is equivalent to a total derivative, and therefore the variation of this gives 0 actually. Then the extra term, here I've put the cosmological constant, give this. And then the variation of the matter action with respect to the metric gives the T mu nu of the matter. And just to state simple things, the definition of this curvature as a two-form, it's not difficult to show that this curvature two-form satisfies an identity, which is that if I take the D, the Cartan D exterior derivative of omega, you don't get exactly 0, but if you complement the Cartan D by things which make it a covariant small d, okay, then you find that this combination of the D's, Cartan D's of the curvature 2 form is 0, identically 0. And this is equivalent to the usual Bianchi identities in coordinate components. And if you do a contraction of this, you find that this Einstein tensor, this combination, is identically divergenceless in a covariant sense. By the way, this is called the contracted Bianchi identity, but actually when Einstein rediscovered it by hard calculations, it was unknown at the time. It had been forgotten. Yeah. Bianchi had found these identities before, but they were lost in the Italian literature, and Einstein got this by direct calculations, and he realized he needed it to have his equation, because this is an identically 0, this is also identically 0, then from Einstein field equation, you get the equations of motion. And the problem of Jacob was to try to do the reverse. If you assume that you have the conserved T mu nu, can you get also the left-hand side of Einstein equations? So,
yeah, and your question, you mean the variation of the action?
Yes, sorry, you're right. It's a variation of the action. Yes, sometimes you write it of the Lagrangian density, it's just shorthand. Okay, just to, so this ends up the definition of general relativity. Now we are going to talk about tests of general relativity. And because general relativity has two separate postulates about how gravity couples to matter and how gravity couples to itself and propagates, there are also two different types of tests. And now I will talk about the tests, the experimental tests of the coupling of the first postulate, that is to say, of the coupling between matter and gravity. Because one can also, a consequence of all the definitions of last lecture, which was how to couple minimally to all the fields of the standard model curved metric G mu nu, is a theorem which is originally due, I guess, to Riemann, which is that if you have a curved manifold, in general you can represent this curved manifold in arbitrary coordinates, but then locally around one point you may find better coordinates, okay? So in general a manifold can be represented by arbitrary coordinates. Then you can look for a coordinate change, so new coordinates, capital X alpha, near some point, which is obtained by an expansion. So I can put a constant which is not important, and then I can put a matrix first order, then something second order, alpha mu nu, x nu, plus higher order. And then I can look for all the possible Taylor expansion of a coordinate transformation to simplify as much as possible the curved metric, g mu nu of x. After transformation, it becomes some metric g alpha beta in the coordinates x, gamma. And then what you find is here you have enough information here, in fact more information needed to transform at the point you are interested in an arbitrary metric g alpha beta to the Minkowski metric. Then if you look at first order in deviation away from this point, you find that you can put all first derivative of g equal to 0, but you cannot do that at the next level, at the level of terms order of x square, second order deviation from a point. You have something remaining, and in fact what remains, the incompressible information, is the curvature tensor, which if it is non-zero in the first coordinate system is non-zero in the second coordinate system. So yeah, but this means that around each point you can reduce the geometry in some coordinate system to something which looks like Minkowski, not only to zeroth order but to first order also. So it's called an osculating space-time. So it's not only, if you have like a curved thing, it's not only to say that I have something which touches this point, but it's something which in a sense gets a better contact with it, like an oscillating circle or something like that. So it's the highest kind of contact you can have at this point.
So torsion should be equal to 0.
Yes, this was always assumed there. That's the part of the minimal coupling. And actually this property, as was proven by Fermi, Enrico Fermi, in the first paper, I guess, of Enrico Fermi when he was a student at the Scuola Normale Superiore in Pisa. He was 21 or something like that. He proved that this cancellation of the fact that the metric is equal to Minkowski metric not only at a point but also the derivatives are 0 is true along an arbitrary line in a curved spacetime. So if I'm in a curved spacetime, I take a line, arbitrary line, then there exists a coordinate system around this line such that all along this line the metric along the line is equal to the Minkowski metric, and the first derivative of the metric are 0 around this point. So, and actually there is like a reverse statement. This statement that all the couplings between gravity and matter can be made to look like nothing, because remember the Lagrangian depend only on the metric g mu nu and the first derivative through the connection. And I should say that the result of Fermi, I can also define a frame, that is to say I can define a field-bind, a moving frame in the sense of Cartan, such that the covariant derivative of the frame, like that in my notation, would be 0 all along one line in space-time. Okay? And this means that all the couplings that were introduced in the Lagrangian of the curved space-time, they are equivalent to being in the Minkowski space-time, which has immediately physical consequences, because it means that essentially all along the world line you have effaced the external universe. I mean, here you are considering a physical system like an atom or a laboratory apparatus, which is embedded in the gravitational field created by the Earth, by the Sun, by the galaxy. But by going to this special coordinate system, you realize that the physics of this physical system embedded in an external gravitational field, its action and its equations of motion, as long as there does not come curvature tensor in the equation of motion, will be equivalent to equations of motion in a Minkowski spacetime. And this has immediate consequences. So it's called the property of effacement. It's also called equivalence principle, but there are many meanings of, so let's call it effacement of external gravity around a world line. So this is true for a system which has a small size, spatial size with respect to the external curvature length scale. So the consequence of this effacement is the outcome of any local non-gravitational experiment if it is referred to local measurements, things you can measure in the space-time around here, and therefore, for instance, in this coordinate system, will not depend on, will only depend on the information in the Minkowski metric, which means it will not depend on where and when it is performed in the universe, and it does not depend, for instance, on cosmological expansion or the presence of the sun or whatever. And this has immediately many experimental consequences. So here what I'm stating is that the first postulate of the minimal coupling of matter to gravity has immediately, it predicts things. It predicts the constancy of constants, how people say, which means that all the dimensionless parameters like the fine structure constants E square over h bar c that you know 1 over 137.035999679. I'm just copying, so that's easy. With an error bar, I should quote it 94. This thing should be the same if you do the experiment here in the Earth or in a faraway galaxy. If you did it 10 billion years ago or in the future, you should always get the same value. Same thing if you take another dimensionless parameter that appears in the physics of the standard model, like at some low energy level, the ratio of the mass, let's say, of the proton to the mass of the electron, okay, which is 1836, etc. So this is a prediction of the minimal coupling of general relativity. Now, experimental tests. This has been tested by many experimental data. Some of them are famous and intellectually interesting, which is that in Gabon, in a site which is called Oklo, 2 billion years ago, a natural fission reaction took place in the ground. In fact, it was deep in the ground, but this thing has been lifted by geological movements, and now it is up in the ground, and this is an uranium mine. And by studying the results of this uranium natural fission reactor 2 billion years ago, you can go back and give constraints on how these things have changed in the meantime. And also, the type of limit you get is that the fine structure constant has not changed with respect to itself by more than a part in 10 to the minus 7. Okay, so you know that some constant 2 billion years ago was the same as today to 1 part in 10 to the 7. You can give very strong limits also on the ratio of the quark mass to the lambda QCD. Now, you can also get limits from observing astronomical spectra, for instance, because by definition, fine structure constant is something you can measure in the spectra of atoms. And here, you can observe atoms which are, so either emission spectra or absorption spectra. You can observe atoms which are in very far away galaxies at some redshift. And one of the best measurements, for instance, is the fractional variation of the proton to electron mass ratio at a redshift of order 2.8, which starts being sizable in the universe. This has not varied by more than 3 × 10⁻⁶. Okay? And recently, atomic clocks have become so good that it is possible by comparing various atomic clocks based on different transitions, and some of them based on various hyperfine transitions, others on optical transitions, others linked to the Bohr constant if they are linked to like H masers and things like that. And when you compare all of them, so a set, an ensemble of atomic clocks, so what you do, you have 2 atomic clocks, and you compare their frequency outputs, so it's a ratio of 2 frequencies, and you look at whether this ratio of frequency is constant in time or drifts. This is a way of measuring whether the fine structure constants and other constants drift in time now. Not billions years ago, but this is a test on the variation of constants today. But the limits are now so good that they compete with this. In fact, they are better in a sense. For instance, one of the limits is that the fractional variation, so ln means natural log of the fine structure constants, alpha electromagnetism, per unit of time, okay, per year if you want, is equal, from some recent measurement, minus 2.5 plus or minus 2.6, so it means compatible with 0, 10 minus 17 per year. So you see, it means that on the age of the universe, 10 to the 10 years, this is a part in 10 to the 7, okay? So it's really a very stringent limit. So this was a first consequence, okay? Yes?
Alpha is measured with which accuracy? 10 minus 9 or what? Because
No, this is 6 here.
No, I mean alpha, which you wrote. 1 divided by
This is
137.
inconsistent.
It's 10 to the 11, 10 minus 11
minus
alpha.
11.
Yes,
So it's measured with accuracy 10 minus 11.
but its variation is known to, but has varied by less than 10 minus 7 in the age of the universe, okay? It's known today to 11 digits. So, yes, so let me write here. Second thing, the second consequence of this universal coupling between gravity and matter. So the first consequence, so let me repeat again. So the basic idea is locally in a curved space-time, I put a certain physical system, I couple it to the external gravity. But one is saying, actually, this coupling is like locally fictitious. I am like in ordinary Minkowski spacetime, okay? I can erase the external thing. And therefore, locally, physics should be like in the standard model in special relativity. So a second consequence is I should have local Lorentz invariance in the sense that although I am in a spacetime where there are special directions, like for instance, the next galaxy is in a certain direction. I can see the Great Wall here, I mean, especially in Jerusalem, and which are like special directions. Locally, I should not see any special directions, and I should not see also any special boost frame, okay? There should be isotropy of space, so no special direction, and also boost invariance, no special Lorentz frame being special, okay? And it's useful to think what could have gone wrong, okay? Like for instance, why there are no special directions is, we said last time, when I have a fermion, I couple it with, a certain Dirac operator, but the Dirac operator means there is a Clifford algebra. Let me put here a mu index to say that this is in space-time. And then there is a metric associated to the propagation of some fermion. So the kinetic term of the fermion moves in a certain metric, okay? But the other particles could move in a different metric, okay? So there could be, for instance, a metric that could be a metric for the electron, a metric for the proton. There could be the electromagnetic field thing, F mu nu, F alpha beta, as also a metric, square root of G mu alpha, G nu beta, okay? So this means the photon propagates in a certain metric. So GR says everybody propagates in the same external metric, but there could be violations. There could be the photon could couple to a certain metric which is different from the metric which couples to the electron. And if there were a difference between two metrics, you find that there would be violation of isotropy. For instance, just to explain this.
Who would couple to theta mu nu?
Sorry, theta, what is theta mu nu?
T mu nu.
T mu nu.
Which of these G's that you imagine would couple to the mu?
Yeah, there would be relations between G's. Here, I'm outside of GR. I'm just saying that in GR, it's the simplest minimal thing. So locally, because there is one metric and I can inface this metric, it is like Minkowski, nothing. If I had initially several metrics, between two metrics I have special directions, okay? Like for instance, if I can reduce this metric to the form Euclidean metric, then this one will be Euclidean metric plus a tensor, okay? And then when I write, for instance, let me write the Hamiltonian for a very simple electron going around if I have Schrödinger equation for an electron going around the proton, okay? The Hamiltonian is usually this, okay? Minus E squared over R. And this is isotropic. It is invariant under rotations. But why is it invariant under rotation? Because this thing is the metric in which the electron propagates, okay? This thing is the inverse of the propagator coming in the kinetic term of the electron. Why? This thing is the green function. This thing is the solution of the metric coming from this thing. It's the field equation here, which says that the green function is 1 over r, okay, in a certain metric which is the same. If I had the difference between the two metrics, then this r would be like delta ij plus hij xi xj square root, okay? I would have something anisotropic, okay? And then I would see that. And I'm mentioning this because people have looked at how the isotropy, because there would be a quadrupolar shift. You see, if you expand this, this means I have the variation of the Hamiltonian due to the fact that I am not coupled universally to the same metric, which is of the type, if I expand this thing, I get 1/2 of E square hij xj over r cube, a quadrupolar coupling, okay, of the electron or any particle moving in an atom, things like that. And therefore, you can look for quadrupolar shift of energy levels, and they have been looked for in nuclear energy levels. And I'm mentioning this because the conclusion is that any of the various metrics that enter there cannot differ by more than something of order 10⁻29. It's one of the highest accuracy tests of physics, saying the isotropy is at the level of 10⁻29. We need to couple everybody to the same metric. Now, there is a third consequence, which is, in a sense, the one that Einstein used as stepping stone for inventing general relativity, which is that if indeed locally I can efface the external gravity and I say the coupling of my material system to external gravity is like in Minkowski spacetime, then in Minkowski spacetime the center of mass of a system goes in a straight line. Okay, the center of mass, let's say, of an atom just satisfies the equation that its second derivative is 0. Okay, so locally I know that any body follows just a straight line. If I go back from the coordinates here, the local coordinates that effaced locally the value of g mu nu, I find that this equation becomes the geodesic equation that I have not introduced, but let me introduce it now, which is this one, that the second, it's the second covariant derivative of the position, or if you want the covariant derivative of the 4 velocity, is equal to 0. Okay, so so this effacing principle says that all particles should, if they are evidently electrically neutral, if they don't have locally a force, they should satisfy the same geodesic equation, so they should all fall in the same way, which was the starting point of Einstein and of Galileo before. Yes, this has been tested to high accuracy. Let me quote just 2 recent results. I mean, the group of Adelberger has been working for years on it, and one of his most impressive results is that the fractional difference in acceleration, in free fall acceleration. So you compare a mass of beryllium to a mass of aluminium, and you let them fall. I mean, they are on a torsion balance, but you see with which acceleration they would fall if they were not the torsion balance, and you find that the fractional change in free fall acceleration is equal to minus 0.7 plus or minus 1.3, so it's consistent with 0, 10 minus 13. Okay, so a part in 10 to the 13 now, which is better than what it used to be years ago. All bodies fall in the same way, and the same thing has been found to be true using lunar laser ranging for the motion of the Earth and the moon and the Earth towards the sun. In the solar system, we have the sun, okay? We have the Earth, and around the Earth, the moon is going around, okay? But seen from this system, the sun is an external attractive force, and the moon and the Earth fall towards the sun, okay? If they did not fall exactly with the same acceleration, there would be effects that you would see in lunar laser ranging, and they have not been seen. And the conclusion is that the fractional difference in the free fall acceleration of the Earth and the Moon towards the Sun is also of the order of 10 minus 13, plus or minus 1.3 times 10 to the minus 13. Okay? And we will rediscuss this experiment later because it is a test not only of the coupling of matter to gravity, but it contains also a component about the self-coupling of gravity, okay? The coupling to the self-gravity of the body.
Does it also say something about the dilaton?
Yes, okay, yes, that we will discuss later, yeah, that there is a limit, that the dilaton couples less than if it exists. Yes?
About the coupling of gravity to gauge field to electromagnetism, is there a way experimentally to exclude the dBi coupling?
So for this you need F4, I mean high intensity of the field. So it's a limit on, you mean the alpha prime, on the limiting strength.
Well, you have to introduce some dimensionful scale.
Yes.
It's limited in ordinary electrodynamics, but
yes, I'm not, I don't know the precise numbers. There should be limits, okay? Because people, for years, they have looked for the QED effect of the Heisenberg-Euler-Lagrangian, which is of this type, okay? And I think they could never check it, actually. So you don't see even this, which is not dBi, okay? It's not the same.
On the scale of the dBi, but I wonder whether the coupling to gravity can be...
But you mean coupling with R or coupling dBi? You mean dBi for gravity?
The square root of, the determinant of F plus G as the coupling of F and G.
But that would not change the gravitational sector, only the F. Okay, let's discuss that separately. I want to come back to the fourth. So now I lost the. This. It's there. Yes, thank you. Yes, please take.
Also,
Yes.
For instance, this kind of the same gravitational constant or not, the effectivity can depend also on the scales which you mentioned, right?
Yes, here I am discussing long range.
Long range, but what are the scales? Because typical scales.
It's the scale of the experiment. If you are talking about the fall of the Earth and the Moon towards the Sun, you need the range to be bigger than that. In Adelberger's experiment, he's making tests not only long range but also short range using hills, around the lab. Okay, so he has also less strong limits on the existence of extra interactions. Okay, I discuss here the long range things. Okay, now the fourth. So we are still discussing only the first postulate of general relativity. Okay, and its experimental consequences. We have already said that there were already 3 consequences immediate of this minimal coupling. There is also a fourth consequence, which is the universality of the gravitational redshift. So I have to explain a little bit why, which is also something Einstein found early on. And the idea is the following. So we have just seen so I have not used Einstein's field equations here. Just the first part of the of general relativity was implying that any body, neutral body, should follow this equation, which is the equation of a so-called geodesic. It's called geodesic. Why? Because it is in space-time. This equation describes a line such that the tangent vector to this line, let's call it u mu, it's the unit tangent vector to this line, is parallelly propagated. If you write the equation that the covariant derivative of this vector u along itself, you find that this equation says that this thing is parallelly propagated, does not change in length, does not change in direction. Okay, so this is the closest analog of a straight line. And this equation follows from the following action. No, sorry. This was not a question for me. This equation, being the analog of a straight line, as an action, it comes from writing that it is the minimal length, or let's say the extremal of this action with a minus sign, which means minus MC integral of square root of minus G mu nu x lambda dx mu dx nu. I can take any parameter P along this word line. I take a word line, I take a parameter P, so x mu is a function of P. Here tau was the proper time, this thing, dP. Okay. Now if you take this action and if you write, although Jacob does not like that, the Euler-Lagrange derivative, if you vary it, you will get an equation which is this equation. Therefore, you know that particles follow this, okay? But we also know that particles follow according to Newtonian gravity. So this should tell us something about, I mean, there is a connection between any theory of gravity has to be consistent with Newtonian gravity. So let us look more precisely at this thing. If I, you have to remember that x0 is ct, okay? When you use ordinary units for time, the zero component you put a c and the other is just spatial coordinate. When you do that, you find that this action becomes integral of dt square root of minus g00 minus 2 g0I vi over c, where vi is the velocity, vi is dxi by dt along the considered word line, minus gig vi vj over c squared. Why am I writing this? Is to say that Newtonian gravity follows from the action S Newton is integral of dt of the kinetic term minus mv square, okay, minus the potential, but the potential energy. But if you introduce the Newtonian potential U, U equal the sum of g times the mass divided by how far this mass is, okay, the Newtonian potential with a plus sign. The potential in the energy sense is minus u, okay, minus mu. That's why minus minus is plus. That's why the action has a plus, okay. And therefore, this thing should reduce to this thing. There is a c square here, and there is a 1 over c square here. So when you look at things, you find that to reproduce Newtonian gravity, it is enough that g00 is minus 1 plus 2 over c square, the Newtonian potential, plus something smaller, okay, and that g0I is smaller than something, okay, smaller than 1 over c square, and that the spatial metric gij is the Euclidean metric plus something which is 1 over c square that you don't know. So any theory of gravity, if described in a curved spacetime, should have that the 0, 0, the time component of the curved metric, should differ from the Minkowski minus 1 by 2 times the Newtonian potential. This is something which has to be true because of Newtonian gravity. That you can prove as a exercise. And because of this, even I've still not used here Einstein field equations. Einstein field equation will have to satisfy this constraint, and it will, okay? But for the moment, any theory of gravity, if it couples universally to matter, should satisfy this. And if I have this property, so I have lost it now because I have it here in my hand. Now, I can do, if I am in a space-time, and I have 2 word lines, and I have clocks moving along 2 word lines, so the clock 1 and the clock 2, because of the universal coupling that is embedded in general relativity, I know that the clock locally, the reading of the clock locally will be given by the proper time, d tau, which is 1 over c ds. So where ds square is g mu nu dx mu dx mu. So I have a curved space-time. I have this invariant, invariant ds square. And locally, it's like in special relativity. So if I take the absolute value of this and I take the square root, this should give the proper time along any clock. So if I have 2 different clocks, I also know something about what will happen when I compare these two clocks for the following reason. If I am, for simplicity, in a time-independent gravitational field, like on the Earth, I will discuss why, although the Earth moves, it is still stationary in some sense. If you do the computation of what will be the proper time that the second clock will measure with respect to its own beat of the emission of crests of ticks sent by the first clocks, you find by an easy calculation that the emitted time interval coming from the first clock but received at the position of the second clock divided by the proper time of the proper clock at the emitted region, which is this, you find that because, yes, so I have to say that the connecting photons, okay, locally they have, again, because of this principle, they are like in special relativity, so they also follow a geodesic equation, but now it is a null geodesic, so I have to say that I can connect the two things by computing the motion of a geodesic between the two, but that will, if I am in a stationary situation, that will give like a constant coordinate time between the two, and when you do the calculation, you find that you can compute the thing by just using G00. So the knowledge of this thing gives me the redshift, I mean the clock comparison between two clocks located at different heights in an external gravitational field, and you find that this is the external potential ux1 at position 1 minus the u at position x2, okay, plus smaller terms. And you see, so still again the first postulate of general relativity, I have not used field equation, just the Newtonian limits, predicts that when I compare two clocks, they should not mark the same time if I compare a clock here at a different height in the potential, and the computation gives a coefficient 1 over c squared with a coefficient 1, which is a prediction, okay? And you can do experiment and test whether the coefficient here is equal to 1 or not. This has been first done, this has been done many times, okay? But still the highest accuracy comparison is an experiment done by Vesso and Levin in 1978, where they compared an hydrogen maser clock, which was sent in a rocket 10,000 kilometers up. So 10 kilometers, 10,000 kilometers is a lot. I mean, it's higher than the radius of the Earth, you know. So you send a rocket up, something like that. And why the H maser is up, you compare it to an H maser which stayed on the ground. And they could verify that this coefficient here, 1, is equal to 1 to a part in 10 to the minus 4, okay, which is maybe less impressive than the others, but still interesting. And I just want to mention that recently people have succeeded in the laboratory in having ultra-stable clocks which have now a frequency stability, delta nu over nu of the clock, which is equal to 1.6 10 to the minus 18. So a stability of a clock of 10 minus 18 means now that if you take this atomic clock and if you raise it by 1.6 centimeter, you see the redshift. So this becomes really impressive, you know. You can see now Einstein redshift on 1.6 centimeter to the 50% accuracy, okay, but still, okay. If you do it on higher things, you will get a better test. So the conclusion of this discussion is the first postulate of GR, that there is a universality of the geometric coupling of matter to the same external metric G mu nu, I mean, has been checked to high accuracy in many different experiments, okay? So this is a part of GR that is difficult to touch. So now let me continue with this. Now, let's discuss tests of the field equation. So, up to now, yes?
Bending of light, okay, people will making further measurement after Eddington for sure with bending of light.
Ah, yes,
So what is the accuracy now?
I will discuss this now, okay? Because I want to say this way, so I have not discussed the field equations up to now. remember in GR there are two sides, okay? How matter couples to gravity, and this is well tested. Now we go to the other part, which is the part of Einstein's action, which is the Einstein-Hilbert action. So let me maybe move this. Now we want to test, is this part a correct description of gravity? Now this part, it implies Einstein's field equations, okay? So now we need to solve Einstein field equations and do computations and make predictions and compare two experiments. And indeed, in this thing, one will also solve not only Einstein equations, but various field equations to compare Einstein and contrast to other predictions, okay? But we will start by discussing the solution of Einstein's equations. Now,
For light width you need just metric as plus.
but you need more than this. You see,
Yeah,
I had written only the Newtonian limit, so I cannot discuss light bending
so
yet.
G,
I need the spatial metric also, which really depends on Einstein field equations. So let me discuss this quickly. Eliezer, you are leaving? No, okay. How much time do I have? Lots of time, yeah, but still, no, nobody wants to say too late. Okay, so Einstein field equation. We are going to show how you get interesting solution of Einstein field equations. I have put the cosmological constant just in case because of Slava's lecture, but for all experiments I will discuss, the numerical value of the cosmological constants today is such that I can either neglect it or say I put it on the right-hand side and then I don't discuss it anymore. So we will solve Einstein equations without a cosmological constant. Let me mention that there are two ways of writing Einstein equations, this way, or I solve for the redshift answer. Then Einstein equations look this way. R mu nu is equal to 8 pi g over C4 times T mu nu minus 1 over the space-time dimension minus 2 T g mu nu, where T is the trace with g mu nu of T mu nu, okay, which comes here. So this is the alternative form of Einstein's field equation, which sometimes is more convenient. When you are in 4 space-time dimension, this coefficient is again 1/2, okay? So one can be confused about 1/2, but this 1/2, like the 1/4 of Jacob, is universal. It is 1/2. And by the way, people discovered, because many people say, I thought myself that Einstein discovered the full field equation with the minus 1/2 only on 25 November or whatever, 1915, okay? In the last rush of the year 1915. Actually, people found that in the notebooks of Einstein in 1912, where he was already discussing linearized gravity, not the full gravity, he had realized he needed the minus 1/2, okay? And he got the linearized Einstein equation with T mu nu and the minus 1/2 already in 1912. So there are two simple limits. If there are two, indeed, like what Mark said, if there are two homework exercises that you should do, these are the two ones that I'm going to indicate. Just that, because after that, I will mention more complicated calculations, where people take years and you don't want to redo that from scratch. But there are simple things if you want to get a feeling, which is how Einstein equations look in the linearized limit when you take a small perturbation around flat space-time. So you should do that type of calculation. This calculation consists in saying, okay, let me take Einstein equations with R mu nu defined by this, gamma, this defined by this, and remember, you have the definition of gamma. Gamma lambda mu nu is 1/2 of g lambda sigma, and here you have three terms. I will just write the last one, minus d sigma g mu nu, and then you have two terms with a plus sign, derivative of g with the indices written in the way that you know. Replace in it g mu nu by the Minkowski metric plus a small perturbation, h is supposed to be small, and work to first order in h mu nu. Like for instance, the inverse metric becomes eta mu nu inverse minus h mu nu with the indices now raised with the eta metric. Okay, if you compute gamma, it's here. This is already of order dh, so this g can be written by replaced by eta. So to compute gamma is trivial. Then you replace gamma here, you take this limit. So actually it's a fairly trivial calculation. And when you do it, just for you to check that you get the correct limit, you should find that the linearized limit of the Ricci tensor, the lowest approximation, is equal to minus 1/2, open parenthesis, times D'Alembert, with respect to the Minkowski metric of h mu nu, plus certain terms which actually have a very simple structure. So I will write them like that. D mu h sigma nu minus d mu sigma h sigma nu. Okay? So here you have, so this term is like d sigma contracted by the Minkowski metric, h mu nu, and this term is d mu nu, h means the trace, h sigma sigma. So you see this term is like this one, except the mu nu goes here and the sigma sigma goes on the other side. And then you have two more terms with a minus sign, where the mu is sometimes here, and the contraction is things. Okay, so this is the linearized Ricci tensor, and therefore Einstein equations at linearized level is obtained by writing this equal to this. Okay, this looks a bit complicated because all these terms. So the second exercise is to say, if I use, there is still gauge freedom. I mean, the entire idea of general relativity is that it's invariant under arbitrary changes of coordinate systems. So evidently I can try, like Maxwell equation, which is invariant under arbitrary gauge transformation. I can simplify Maxwell equations by going to the Lorentz gauge. Here I can go to the analog of the Lorentz gauge. The good definition of the analog of the Lorentz gauge is d nu square root of g. If you work at the nonlinear level equals 0, okay? If you linearize this equation, you will find that this means that d nu of h mu nu minus 1/2 of h, eta mu nu equals 0. So at the linearized level, it looks like a Lorentz gauge condition, you know, the contracted derivative, the how is it called, the divergence of something equal to 0. What if this is imposed to be 0, and you can do that by a gauge transformation? Actually, you can see it here. You see that this term and this term, because they contain d sigma h sigma, they will simplify and they will give 1/2 of h this. But because there are two terms, this term is precisely twice, let me write it, the 1/2 here. So I can put this 1/2 here, this 1/2 here, and then it means that in this gauge, the linearized Ricci tensor is simply equal to minus 1/2 D'Alembert of h mu nu. So now you start seeing Einstein equation in a very simple form. Okay, for instance, Einstein equation at linearized level, they becomes D'Alembert of h mu nu is equal to minus, I put the minus 1/2 on the right hand side, minus 16 pi g c4 t mu nu minus 1 over d minus 2 t eta g mu nu. Okay, so you have immediately Einstein equations in linearized form, and then you can start solving it. And when you solve it, you check that indeed, because of the 16 pi g, you get in the for g00, you will find, if the pressure of the matter is not too important in a localized system, you will find minus 1 plus 2 u over c squared. But now, if you solve Einstein equation this way, you will get more information. You will get what is the value of gij. Okay, when you do the computation, you okay. I will discuss this more. It's just here I am discussing the solution also in the Newtonian approximation when the sources do not move, so that I replace D'Alembert by Laplace. But we will solve it better approximation. But let me mention that this way, because Slava was mentioning this, when you do this computation, you get that the spatial metric is modified by a coefficient 1 plus 2 u over c squared, while the G00 metric had 1 minus 2 over c squared, u over c squared. And light deflection will be contributed by the sum of this term and this term, okay? And we will also discuss.
If Einstein wrote it in 1912, as you say, why he forgot about it? Because really, coefficient.
It's because at the it's because at the time he had, you know, there is this paper of 1912 also with Grossman, okay? And in this paper, there is a mathematical part and a physical part. In the mathematical part written by Grossman, Grossman says the simplest equation we could write for the gravity in vacuum would be Ricci equals 0. And in the physical part, Einstein demonstrates that this is a bad law, that you cannot take this is impossible, okay? And this is impossible because at the time, he was looking for equations where the matter would determine the gravitational field. And why here, this equation, you know, this equal T mu nu minus 1/2 of T eta mu nu, there is still a gauge freedom. So you cannot solve the field in terms, and at the time, although he must have known Maxwell, I mean, it looked strange. He had this famous Hall argument, which is that if in space-time you have a region where you make a coordinate transformation, the development in time of the gravitational field will not be deterministic because something will change. So he was confused with this. He was confused with the Newtonian limit also. I mean, it was difficult to get everything right, okay?
Yeah, so
and because of this, for years he said, no, Grossman is wrong. I mean, we should not use Ricci. We have to use non-convariant field equation. And then he wrote an action which actually is the Einstein action, except that some terms were wrong, okay? Because he surprised...
so trouble was that he didn't know which gauge to use to get right.
Let's not diminish the merit of Einstein. I mean, this is a long... There are books written about this. This was subtle. Let me mention also, just for the historical point of view, that in November 1915, Hilbert wrote also a paper. But you know, but there is a long story about this. It's you will hear about it in the history thing. Okay, it's a very delicate thing. Nobody knows exactly what he did. But what is clear is that Hilbert wrote in it that you cannot have covariant field equations, and he wrote many wrong statements. So Hilbert did not understand covariance better than Einstein, and he was a mathematician. He should have known better than Einstein. Okay, so finally Einstein, with his physical intuition, went back to covariance and the Newtonian limit and everything in November 25, November 18, actually, 1915. Let me, second homework exercise. So the first one I nearly did for you in front of you, okay? But you still need to check that you can solve the metric. There is one solution which often is in textbook discussed to summarize all the comparison between Einstein theory and experiments in the solar system, in the weak gravitational field limit. This is the Schwarzschild solution. Let me just give you a few hints. You should also, if you never worked with Einstein equations, try to use Einstein equations, they are fully written here, and solve for the spherically symmetric case. So, because this solution was found within 2 weeks of the discovery of Einstein field equation by Schwarzschild, and he was, you know, on the front. The Germans were doing something all over Europe at the time in 1916, and Schwarzschild was on the Ukrainian front or something like that, or Crimea, I mean, somewhere far back. And he was an officer, so he had some free time. And when he received the preprints of Einstein, he solved Einstein equations for a spherically symmetric situation, okay? And he found the first solution, which is the famous Schwarzschild black hole. So you should try to do the same thing. We are not at war, or maybe here we are at war, but take the time. So you look for a general spherically symmetric solution of the following type. You have a function in front of dt square. So as you noticed, I don't use the same signature as Slava. Slava uses the Russian signature, and I use the Western signature, dr square. And then in general, here there could be a third function, d theta square plus sine square theta d phi square, okay? But there are several choices you can make, because once you have this thing, you can always change the radial coordinate r. I mean, Einstein equations are invariant under change of coordinate. By the way, when Schwarzschild had to find a solution, he had only the field equation of Einstein, not in the final form, but in a form which was gauge fixed, and he had to use a coordinate system where the determinant of the metric was 1. That's why he got actually a solution in a form, but he still wrote the Schwarzschild solution.
Also, he did assume that there could be time dependence.
Yeah, so let's assume Schwarzschild assumed that. It's not Birkhoff who did that later. We assume spherical symmetry and time independence. I mean, the idea was to find the exact solution around the sun in the solar system, okay, or around a given star. Now we know that there is a gauge invariant, so we can change the radial coordinate to whatever we want. So we could do many things. One convenient choice is to fix that this coefficient is just r squared, so that the angular factor is just the usual flat space-time thing. Yes, Joe?
How can the term do you want to use the sine theta?
Aha, good. He was sharp, you know. Indeed. So he had to use, let me give you the thing, theta and minus cosine phi, okay? So he used coordinates so that d theta, d cosine phi was already, okay? And then for r, he had to do something else. Okay, and at the end, he changed, yeah. But he had to do this trick, okay? They knew tricks at the time, these people. But let's do it in the modern way. So let's impose that this is r squared, and Einstein equations are independent of any coordinate system, so you can compute the Ricci tensor in r theta phi coordinates, okay, in polar coordinates. And the trick is to, so let me, I did not define this. This object is the Einstein tensor. It's called the Einstein tensor. There is, alas, no uniform notation for the Einstein tensor. In France, usually, Lichnerovich called it S, okay? Many people call it E for Einstein, but some people call it G mu nu, okay? I will use G mu nu because it's like the American way of doing it. It's not convenient in string theory because you want to keep capital G mu nu for the, worldsheet metric. Anyway, let's call it for the moment G mu nu. The various field equation you could write is the time component. Let's also use one index up, one index down because it's more convenient when you write equation. You have the TT component, the radial component. You have the theta component and the phi component. You find that this is equivalent to this one. Okay. Then you find that because of the Bianchi identities that I mentioned, the Bianchi identities is nabla mu of G mu identical to 0. These equations, this equal to 0, are consequences of these two equations. So we can forget about these equations before the calculation. So now we have two equations for two unknowns. Okay. And when you it's convenient to write this combination, so I give you the nice combination. If you compute this combination of these two equations, you find that they imply that the derivative of the product AB is 0. And therefore, the product of this function A of r and B of r is a constant. This constant you can put to 1 because you have a scaling of time that you can still fix. So this equation rather easily gives you the constraints that AB is equal to 1. And now you can write the other equation, which is GTT equals 0. And this equation, GTT equals 0, when you write it explicitly, it gives that the radial derivative of r divided by the B function is, no, it's not, I don't mean is equal to 0, I mean is equal to 0, yes, which means that, is this what I mean? No, it's equal constant. Yeah, I get a second order derivative, so I mean equal a constant. And let's call this constant minus 2 small m without prejudice about what is the value of small m. And therefore, now this and this gives that the A function is the inverse of the B function. And this equation tells you that the B function is 1 minus 2m over r. Okay? So, so you can solve Einstein equation easily. And then when you compare this to the Newtonian limit, which was saying that G00, when you change its sign, is 1 minus 2 the Newtonian potential, you conclude that this constant of integration, small m, you can call it the mass of the central object multiplied by Newton constants divided by c squared. Okay, this is just a way. So this way, so you should try to do this exercise. Numerical value is, if you have never seen that, for the sun, this coefficient small m, that is to say gm sun divided by c squared, it is roughly 1.5 kilometer. Okay, it's 1.477 kilometer. So just to have an idea, probably I should stop now. No? Are you sure? At what time am I supposed to stop?
You enter 55:30.
I have 5:30. Okay, good, good. I thought, good, so I don't stop.
But you can stop.
No, I don't want to stop. I don't want to stop. What I want to do two things. I want to say the traditional textbook discussion of experimental tests of general relativity that I will not do in detail consists in saying, okay, let's model the structure of the solar system by one central body, the sun, its curved space-time around him, which is given by the Schwarzschild thing, and then let's discuss everything here. But this is an approximation which is not sufficient by modern standards. So we need to do better than this, but I will still mention one practical thing that in doing this, that is to say, in discussing the motion of the planets and all the solar system tests around the sun, okay, what you have is that you have this central object, which is the sun, and it has this curved geometry around it, given by this formula, okay? And then you want to discuss the motion of the planets. So the planets will go around the sun, okay? There will be, as we know, there are several planets, okay? And each planet follows a geodesic. So to discuss the motion of the planets, you should solve the geodesic equations. And also, when you do measurements, like you send a radar signal from one planet here and then back, okay? You need to model light rays in the solar system, but we have seen before that light rays also follow null geodesics, but they are null geodesics. And the simplest way, what I want to say here, is to do these calculations is like in Landau-Lifshitz, which is, by the way, Landau-Lifshitz is still probably the best book to learn general relativity in a few pages. You need to complement it.
But I think you did better than Landau.
Yes, but to go still, you go quite far still, okay? If you don't want to become an expert on it, is to use Hamilton-Jacobi equation, okay? Let me mention this because we will go beyond Landau-Lifshitz, but we will go back to Hamilton-Jacobi equation later, which is still very efficient. So let me remind you of how you solve the geodesic equations by the Hamilton-Jacobi equation. What you do is you write the mass shell condition for a particle of mass. So mu, let me put mu bar to distinguish from this index, okay? And mu bar will be non-zero if I have a massive particle like a planet. And if I consider a photon, I can take the limit where mu bar tends to zero also for the motion of a photon. So you write essentially the mass shell condition, you know, p square equal minus the mass square, okay? P square plus mu square equal to 0. And the condition that p mu, the covariant p mu, is the partial derivative of the action, the Hamilton-Jacobi function, with respect to x mu. So it gives you a partial differential equation for S, which is that you write in the Schwarzschild spacetime. So it is separable. You can separate angles, radial time, and this way you get immediately to the essence of the results if you want to discuss the perihelion precession of planets and also the motion of light rays and the light bending, for instance. You write the Hamilton-Jacobi equation, and then you get immediately an integral for the light bending, okay? But this is not what I want to do because I want, let me put the minus mu square here. I want to discuss, so this is, let's say, the textbook treatment of, this would be the textbook treatment of experimental tests in the solar system, okay? Now, let me discuss modern things because actually the solar system is not just the sun and the planets. The solar system is an n-body system, and today we do more complicated measurements than at the time of Einstein and Schwarzschild. Like, for instance, there is the Earth, there is the Moon. The Earth and the Moon have quadrupolar structures. They have a multipolar structure. They go around each other. Around the Earth, there are satellites, and you want to do the relativistic dynamics of the Moon around the Earth, of the satellite around the Earth, but the Earth and the Moon are also going around the Sun, and they exchange radar signals with all the planets. So you need a theory of n-body systems in GR. So let me discuss quickly how one, in modern language, one is treating the n-body problem in GR. Okay, the Schwarzschild solution is solving the one-body problem in GR. By the way, I remember a very beautiful talk by Paul Townsend where he was saying the more you advance in physics, you know, Newton could solve the two-body problem exactly. Okay, in Einstein you can solve the one-body problem. In quantum field theory problem, you have the zero-body problem, which is a vacuum. In string theory, you don't have, you have the minus one-body problem that you have sometimes, okay? And, okay, and maybe it can go down even, okay. So the n-body problem was first attacked by De Sitter, actually, by Drost and De Sitter in 1916, and there were mistakes. For years, there have been mistakes in this problem. And then when it was applied also to the real life, people introduced new mistakes because there is the problem, which is the following. The usual treatment of general relativity n-body problem is to say, okay, I have Einstein field equations that are still here. I want to, they are written in a coordinate system. So let me take one, we are discussing here the solar system. The solar system is weakly curved because when you put numbers, yeah, I should say that. For instance, G00 equal -1 plus 2u over c squared. The value of 2u over c squared at the surface of the sun is 10⁻⁶. So we are talking about a deviation from flat space-time at the sun, which is the strongest field, by 10⁻⁶. If you are at the surface of the Earth, it's 10⁻⁹, okay? So we are talking h mu nu is really small. And therefore, you could say, okay, I take a coordinate system, small x mu, because I am in a weakly curved region of space-time. So there will exist a coordinate system which exists globally. And in it, I will have one body here, and two body, and three body, whatever. And I will discuss the motion of the n bodies in this common coordinate system. Okay? It looks like a good idea. Actually, it is a very tricky idea. I mean, because how do you define the center of mass of these bodies? These are extended bodies. And then these bodies, they will be actually deformed because the Earth is big and it moves. So there is a Lorentz contraction for sure, but there must be the analog in GR of a Lorentz contraction due to the curved space-time. How do you treat that? How do you define the center of mass? And this introduced many errors, and even people in the codes at JPL, for instance, at some point they had forgotten that the GR effect of U meant that there was a 1 centimeter contraction of the Earth, for instance, and then the radar signals were wrong by 1 centimeter and things like that. So this old approach where you use only one coordinate system or one coordinate chart, for some reasons it is better to replace it by a different approach to the n-body problem, which is the following. This is a multi-chart approach. And this is an approach that actually you use in Newtonian theory, because in Newtonian theory, when you discuss the motion of n-bodies, you take a coordinate or a frame attached to a certain body to discuss what happens around this body. For instance, the quadrupole moment of the Earth is defined in a frame attached to the Earth, okay? And also for the quadrupole moment of the Moon. So you use coordinate system for each body. But in Newtonian theory, it's easy to write coordinate transformations for each coordinate. It's just a translation, time-dependent translation. In GR, it looks much more complicated. But there is a simple way of doing it, which is the following, and I want to describe it in words at least. So what you want is around each body, you want to define coordinate system, let's say attached to the body, like body 1, there will be a coordinate system x1 alpha, and body 2, there will be a different coordinate system x2 alpha attached. So this would be like geocentric, you know, centered on the Earth. This should be like selenocentric, centered around the Moon, or barycentric you can put. And then barycentric, and then you use a coordinate system for the rest to embed everybody in the same, because you want also to be able to contact what is the motion, I mean, to connect the motion of the satellite around the Earth to the motion of the Earth around the Sun. So you need also a common coordinate system. So finally, you need also a global coordinate system x mu, like in this thing, but complemented by local coordinate systems. Okay? But now what looks complicated when doing that is you say, but if you do that, this means you will have to solve Einstein equations not once, like here, but you will have to solve it n plus 1 times. You need to solve it again in each frame. But there is a very simple way to do that, and that's what I want to mention, is, and this is something that you don't find yet in textbooks, okay, but I hope in the future it will be in textbooks, because it's really simple, is you should use a special exponential parametrization of the metric, which renders Einstein equation linear at the level we are interested in, because we are interested in solving Einstein equations. Let me write yes, what we want, all tests of Einstein equations in the solar system, that will not be true for tests I will discuss later in binary pulsars and things like that, okay? They only need to know Einstein equations to the so-called first post-Newtonian approximation, okay? Which means that G0 should be known not only the 1 over c square term, but also you should know the 1 over c4 term, which is, so this is of order, but we will be more precise, the Newtonian potential plus relativity correction, and this will be of order the square of u. So here you will use nonlinear structure of Einstein equations. You know, the fact that when you write Einstein equations in the Lagrangian, it's not just quadratic, there are cubic terms in Einstein equations. For the other components, it will be enough to know G0i to 1 over c cube and Gij to 1 plus the 1 over c square. So I am using as expansion the inverse velocity square, which means that it is both G in Einstein equation always come by G over c square. Okay. In Einstein, you have G over c4, but remember this is T mu nu. T mu nu contains energy density, which is actually mass density times c square. So really, on the right side of Einstein equation, I have G over c square, which is one expansion parameter, and I have also velocity square, because here I have like the motion of the matter, u mu, which contains v over c. So I have the 1 over c, which allows to put together two expansion parameters, the small velocity with respect to 1 over c, and the small gravity g over c square, and which also combines the D'Alembertian 1 over c square corrections thing. So all that, the post-Newtonian approximation consists in counting 1 over c square as a small parameter and to work formally in that.
This
So
was the motion of the particle which creates gravitational field, right?
yes, there is
Then
exactly. The planets, they move
but then
slowly.
Light, when you consider symmetric light propagation, you could use the same extension?
Yes, you will lose some accuracy in the sense that you will know light deflection, for instance, only to some
the
first
leading
order,
order.
to leading order,
Yeah.
yes, and not to the next order. For light
So
deflection,
it's
you
one
need to
over
go,
c
exactly.
squared, that's-
But you need higher accuracy on this guy, okay.
Yeah.
So the trick is, instead of solving Einstein equation by putting H00, like you find in textbooks, okay, you write G00 as minus exponential minus 2 W over C square. So you introduce a potential W, or you can call it V, which is the logarithm of G00. If you expand this, this means minus, 1 minus 2W over C square plus 2W square over C4, and you will keep this term. Okay, so the exponential is a way of encoding this square term automatically. G0i, you don't need to do much. You can just introduce some potential, vector potential. And then Gij, you put its prefactor as the same exponential, but with a plus sign. So it's a gamma ij. So you replace the component G0i, G00, G0i, Gij by W, Wi, and gamma ij. Okay? And you plug this in Einstein equations. And then what you find is that to the accuracy you need, gamma ij is a flat metric. And therefore, you can take it as equal to delta ij. And moreover, you can take it equal to delta ij in all coordinate systems, because then you prove that also in these local things, this metric gamma can be taken to be the flat Euclidean metric. So this is dealt with. And now Einstein equations will give you two equations for W and Wi. And the nice thing is that these equations are linear. And because of this, you will be able to solve them in each frame as easily as is any other frame. Let me write these equations that you don't find in textbook. So you find that W, so here, this is what is, I mean, it's in all textbooks, people say that gravity is like gravitomagnetism. There is like a scalar potential and a vector potential, okay? But here it's even more accurate than what you think, because even at the nonlinear level, they satisfy linear equation. The vector potential satisfy an equation of this type, plus 4 over c squared, the time derivative, and then the divergence of the vector potential is equal to minus 4 pi times g, a certain matter density sigma, where sigma is defined as T00 plus T trace over c squared. Now, in cosmology, this thing would be epsilon plus 3p, okay, which indeed appears in one of the Friedmann equations. Okay, that's the one which appears here. And the other equation...
But your equation is not applicable to cosmology.
No, it's not.
You can see
It's not. Yes. But it's still, there are connections. The 3p comes there. We are supposed to make connection between various talks here also, okay? Minus dt di w equal minus 4 pi g sigma I, where sigma I is just T0I with indices up, by the way. Here it's important. Here you cannot put this is the real T with indices up. You cannot put an index up or down, otherwise it's wrong, okay? Because the metric is important here. T0I over C, simply, yes. Anyway, these are components of the T mu nu. And then you get Einstein equations at the level where you include the main nonlinearities. They become a set of linear equations that look a bit strange, okay? There is a gauge invariance in the sense that you test easily. I mean, there is a gauge invariance because I have still not fixed the coordinate system. I fixed the coordinate system only by imposing this, but there is still a remaining coordinate transformation of the time variable. So there is one function, there is like a U1 gauge invariance, which means that these equations, as you can check, is invariant if I change W in W minus 1 over c squared, the time derivative of a gauge function lambda, and Wi by plus 1/4 of the gradient of lambda. So there is a 1/4, okay? So it's not the usual U1 gauge transformation. Or I should have used 4W if I wanted to have the usual U1. But then when you use 4W, you don't get the same Maxwell thing. There is always something which is not Maxwell-like, okay? And it's because the spin is equal to 2 and not to 1, so there are coefficient 4 that appears here and there. But you can use this. So this is a fact. These are Einstein equations to the now one for first post-Newtonian approximation with this gauge transformation. If you want, it's not needed because sometimes it's good to keep the gauge transformation. You can use the gauge transformation to fix something to 0. And in particular, you can fix to dt to the Lorentz gauge type, which is that, you know, d mu a mu equals 0. But remember that the gauge transformation at the 1/4, so it is not Lorentz transformation. But still, yes. If you impose this condition, you find that these equations simplify very much, and I will just write it. So let me forget about this gauge transformation. So in this thing, you find that this equation becomes simply. Now I get the D'Alembert operator. That was not evident here. Okay. Acting on W is equal to minus 4 pi g sigma. So now I get really like Maxwell equations. And the second one is also like Maxwell equation, but because I can neglect the 1 over c squared, I get Laplace of Wi is minus 4 pi sigma I. So you see, this is why we had introduced these definitions, because with this definition, these two potentials, W and Wi, and in the gauge fixing I'm saying, they satisfy Maxwell equations, simply, with the D'Alembert, W and 4 pi. So I can write immediately the solution with retarded potential, or semi-advanced, semi-retarded, and therefore I can write the solution in all coordinate system, and then you can discuss how you transform from one coordinate system to another. And then when you do that, you can do the theory of n bodies with arbitrary multipolar structure and do all the transformations. This has been worked out in a series of papers of myself with Michael Soffel and C.X. Songmin Chu in the 90s. Okay, let me stop here.
So Thibault, W is not just Newtonian potential.
No, it is. In lowest approximation,
No.
it is.
Wait, in laws, but you understand that Newtonian potential cannot propagate with time.
Yeah,
because it's
this thing
just
propagates,
very-
yeah.
This thing propagates. So it
Although
will be
I should say,
either gauge artifact or...
yeah, because this thing does not really propagate. When we will discuss gravitational waves, what really propagates are the degrees of freedom of the gravitational field, which are the two polarizations, okay? And here we are still at the level of the longitudinal graviton
Right, but I do
and
not
gauge
see-
degrees of
yeah,
freedom.
but
So,
I do not see from here why it's not propagating. If it's great
because it's
potential.
still a gauge thing. I have still,
It's
okay,
gauge thing, you see, so
okay.
there should be some-
Still a gauge thing. But it's still useful. Okay. Thank you.